This research delves into the realm of multimodal large language models, MLLMs, and their potential for achieving generalized intelligence by integrating visual understanding into large language models. However, the substantial memory and computational demands of MLLMs hinder their widespread deployment. To address this, the authors explore efficient MLLMs from a distillation perspective, examining what matters for training small-scale MLLMs through knowledge distillation. The authors investigate 4 aspects of knowledge distillation between stronger teacher models and student models: feature embedding distillation, logit-level distillation, affinity-aware distillation, and data-driven knowledge distillation. Their empirical study reveals several interesting results, including that feature-level distillation can improve student results and work orthogonal to logit-level distillation, but is more sensitive to layer position in LLMs. Naive logit-level distillation works well, even better than specifically designed LLM distillation loss. Affinity-aware distillation losses do not work well in various cases, and data-driven knowledge distillation can improve student results by adding teacher-generated and instruction tuning data. The authors propose a simple yet efficient distillation framework, LLAVADI distillation, LLA versus ADI, which jointly distills features and logits, refined by teacher-generated data and instruction tuning data. They conduct extensive studies on various teacher and student baselines, demonstrating that LLA versus ADI can generalize to numerous teacher and student frameworks. The main contributions of this work include exploring the first detailed studies on MLLM distillation, showing that most existing LLM distillation methods cannot bring extra gains for MLLM, and demonstrating the superiority and efficiency of LLA versus ADI in multimodal datasets on various baselines. The research provides a comprehensive understanding of what matters for MLLM distillation, highlighting the importance of joint alignment for both tokens and logit alignment in teacher-student frameworks. The authors also demonstrate that even a 2.7b small-scale model can perform on par with larger models with 7b or 13b parameters by evaluating different benchmarks and proper strategy. Here is a combined summary of the research paper, covering pages 58. The authors present a comprehensive approach to knowledge distillation for large language models, LLMs, in multimodal learning. They introduce 2 primary methods: logit-level distillation and feature-level distillation. Logit-level distillation employs a softmax temperature-based KL distillation approach, where the student model is trained to align its logits with those of the teacher model. The authors also explore the use of Jensen-Shannon divergence, JSD, to balance forward and reverse KL divergences. Feature-level distillation involves aligning intermediate representations of the transformer layer between the teacher and student models. The authors find that aligning only the last layer yields better results than aligning the last 2 layers, which leads to significantly worse performance than the baseline. This is because the last layer contains high-level semantic information crucial for token classification. The authors also investigate data-driven knowledge distillation, where the teacher model generates a large amount of contextual and domain-specific training data. The student model trained with these generated data samples can closely mimic the intricate understanding and cognitive abilities of the teacher model. Experiments are conducted on 6 datasets, including GQA, SQAI, VQAT, POPE, MMEP, and MMBDev. The results indicate that the proposed knowledge distillation methods can improve the performance of the student model, especially in the fine-tuning stage. The findings suggest that aligning only the last layer yields better results than aligning the last 2 layers, and that aligning all tokens can lead to slight performance improvement than aligning only answer tokens. The authors also explore various methods for aligning logits, including KL divergence, logit standardization, and affinity-aware distillation. The results show that KL divergence consistently delivers superior or comparable results in all aspects. Data-driven knowledge distillation is also explored, where the instruction tuning dataset is regenerated using the teacher model or student model. The results show that data corrected by the teacher model performs well in VQAT, SQAI, and POPE, but has slightly declined in MMEP. The proposed method outperforms Distill-BERT in terms of performance. The paper discusses various techniques for multimodal language models, including knowledge distillation, instruction tuning, and visual linguistic pre-training. It highlights the significance of knowledge distillation in compressing large language models, referencing works such as Distill-BERT, Tiny-BERT, and structured knowledge distillation. The authors also discuss the role of layer-wise distillation and task-aware layer-wise distillation for language model compression. The paper explores the concept of visual instruction tuning, which involves fine-tuning language models on visual instructions. This technique has been shown to improve performance on various vision language tasks, as demonstrated in studies like visual instruction tuning and MFT coder. Furthermore, the paper mentions the importance of datasets like Obelix, iConca, and Bench for evaluating multimodal models. It cites works that have utilized these datasets, including Learn to Explain and VigC. Additionally, the paper touches on the topic of object hallucination in large vision language models, referencing a study by Yifan Li et al. The authors also discuss the significance of thought chains for science question answering, as demonstrated in Learn to Explain. Finally, the paper references various other studies that have contributed to the development of multimodal language models, including ChatGPT, GPT-4, and Stanford Alpaca. The authors also mention the importance of evaluating multimodal models using comprehensive metrics, as demonstrated in works like Bench and GQA. Here is a combined summary of the 4 pages. The paper highlights the significance of teacher-student learning in enhancing fast segmentation models, citing the work of Kan Wu et al., who proposed Tiny Clip, a method that utilizes clip distillation via affinity mimicking and weight inheritance. This approach has been shown to substantially improve the performance of fast segmentation models. The authors also reference various studies that have explored techniques such as self-training with noisy student and teacher-student learning, which have demonstrated effectiveness in enhancing model performance and bridging the gap between teacher and student models. The authors argue that current instruction tuning data generated by language models may contain inaccuracies or hallucinations, and propose regenerating the answer to each question using the teacher model, thereby distilling knowledge from the teacher to the student model through a data perspective. This approach is exemplified through a conversation generated by the teacher model, showcasing its ability to provide more accurate and detailed descriptions compared to the original instruction tuning data. The authors then explore the scalability of their distillation strategies by conducting experiments on a combined dataset of 2 million instruction tuning samples, comprising various types of data structured in a dialogue format. They employ mobile LLAMA as their base language model, using the same set of hyperparameters as LLAVA, and train the projection layer during pre-training without employing any distillation strategy. Despite achieving higher results than the baseline, the authors acknowledge that their results still fall short of their expectations and lag behind the teacher model's performance in most evaluation benchmarks, highlighting the need for further research and refinement to bridge this performance gap.